Continuing our work on the homework for rotational motion and angular momentum, let's take a look at problem number 6. Problem number 6 states the following. Suppose a piece of dust finds itself on a CD. If the spin rate of the CD is 500 revolutions per minute, RPM, and the piece of dust is 4.3 centimeters from the center, 4.3 centimeters from the center, which is 0.043 meters from the center. What is the total distance traveled by the dust in 3 minutes? T equals 3 minutes. Now let's do some changes here. We want 180 seconds here. This is good. I already did this change. And then 500 revolutions per minute is going to equal 52.4 radians per second. So theta, in this case, is going to equal omega times t, because it doesn't talk about any acceleration or anything. So this is going to equal 52.4 radians per second times 180 seconds. And that's going to be 9,400 radians, two significant figures. Now d, which is the linear distance, is equal to theta times r, which is equal to 9,400 radians times 0.043 meters. Now, if you put in centimeters there, your answer would just be in centimeters instead of meters. If you do the math here, you get 405 meters as the total distance traveled. Number 7, a gyroscope slows from an initial rate of 32 radians per second, so omega naught is equal to 32.0 radians per second, and it slows at a rate of 0.700, so alpha is equal to minus 0.700 radians per second squared. How long does it take for it to come to rest? So WF is going to equal 0. Omega F is equal to omega naught minus alpha t, plus alpha t, excuse me. That's going to equal 32.0 plus 0.700 times t. And we know that WF here is equal to 0. So if we solve this t, we get 45.7 seconds. It takes 45.7 seconds. Well, how far does it travel? So that's how long it takes for it to stop. How many revolutions does it make when it stops? Again, theta is equal to omega naught t plus 1/2 alpha t squared equals 32 times 45.7 plus 1/2 times minus 0.700 times 45.7 squared. And if you do the math here, you end up with theta being 731 radians. And if you divide that by 2 pi, you get 116 revolutions. So 116 revolutions. Number 9. Number 9 is the last of these simpler problems. Everyday application. Suppose a yo-yo has a center shaft that has a radius of 0.250 centimeters, which will be 0.0025 meters. and that the string is being pulled. If the string is stationary and the yo-yo accelerates away from it at a rate of 1.50 meters per second, what is the angular acceleration of the yo-yo? So A, tangential, is 1.50 meters per second. And the question is, what's alpha? Well, alpha is equal to the tangential acceleration divided by the radius. So this is 1.50 meters per second divided by the radius, which has to be expressed in meters. So the angular acceleration of the central spindle that the string is on is 600 radians per second squared. Now the second question is, what is the angular velocity after 0.750 seconds? So it's asking, if we start with an angular velocity of 0, what is the final angular velocity if we have this acceleration for 0.750 seconds? Well, again, F is going to be equal to omega 0 plus AT, alpha t, excuse me, and this is 0, and so alpha t is going to be 600 times 0.750, and that answer is 450 radians per second, assuming a uniform acceleration. The last question is, the outside radius of the yo-yo is 3.5 centimeters. So the outside radius is 3.5 centimeters, or 0.0350 meters. And the question is, what is the tangential acceleration on that point, at the point of that edge? The tangential acceleration at that point is equal to alpha times the radius. We know that alpha is 600 and the radius is 0.0350, and so the answer is 21.0 meters per second. Number 11. Now with number 11, we're moving into rotational inertia, and we introduce the concept of an inertial moment, which is I. Inertial moment, you have to become familiar with that diagram 10.12, intimately familiar. And we'll be using that quite a bit in upcoming time. Calculate the moment of inertia of a skater given the following information. So the first situation, now we're supposed to assume that this skater is a cylinder that has a mass of 60 kilograms and a radius of 0.11 meters. So this is when she has her arms next to her side. And so the first question is, what is the inertial moment, or the inertial moment, or moment of inertia? For this, if you look on the table with a cylinder, the inertial moment's 1/2 mass times the radius squared. So it's going to be 1/2 times 60 times 0.110 squared. And if you do the math here, you get 0.363 kilogram meter squared. Now the second situation is basically, we now have the similar cylinder here, except the mass of this part of it excludes her arms, so it's only 52.5. And she's holding her arms out, and when she holds her arms out, it approximates what they've called here a cylinder, like the rods rotating on their ends. So it's like you have a cylinder, but it's rotating on the end instead of through the middle. And so if you look that up on the table, that's 1/3, and the mass of these arms is 0.900, and the radius is 3.75. I'm sorry, 0.900 squared, and the mass is 0.375. Got those backwards. And you have 2 arms, and if you do this math, you get 2.34 kilogram meter squared, which is why, well, I don't want to confuse the situation, so I won't say what I was going to say about the change in angular velocity when a person pulls their arms in when they're doing a rotation as a skater. Okay, number 13 says the following. A soccer player extends the lower leg in kicking motion by exerting a force of the muscle above the knee in front of her leg. She produces an angular acceleration of 30 radians per second squared. And her lower leg has a moment of inertia of 0.750 kilogram meter squared. What is the force exerted by the muscle if its effective perpendicular lever arm is 0.19 meters, 1.90 centimeters? So the question is, what is the force exerted? So we've said this before, but the net torque is equal to the moment of inertia times the angular acceleration, which is equal to 30 times 0.750. So the net torque is 22.5 Newton meters. And the net torque is also equal to the radial arm times the force. So the force is going to equal the net torque divided by the radial arm. So it's going to equal 22.5 divided by 0.014, excuse me, 19 meters. And so the force is going to equal 1180 newtons. Let's do one more on this tape before we move to the next one. Number 14. Suppose you exert a force of 180 newtons tangential to a 0.28 meter radius 75 kilogram grindstone. So you have a grindstone that has a radius of 0.280 meters, and it weighs or has a mass of 75.0 kilograms. It's a solid disc. What is the torque exerted? The torque is equal to R times F, which is equal to 0.280 times 180, which is 50.4 Newton meters. The torque is also equal to, so that's A. B asks the question, what is the angular acceleration if what is the angular acceleration assuming a negligible friction? Well, we know that torque is also equal to the moment of inertia times the angular acceleration. So the angular acceleration is going to equal the torque divided by the moment of inertia. The torque we know is 50.4 angular. For a solid disk, it's 1/2 times the mass, which is 75, times the radius squared, which is 0.280 squared. If we do the math here, we get 17.1 radians per second squared. And C says, what if you have a friction force? And the friction force is 20 newtons exerted at 1.5 centimeters from the axis. So the net torque is going to be equal to the torque exerted up here, so 50.4 minus 20 times 0.015, which is equal to 50.1 Newton meters. And then if you put that in here, replacing 50.4 for 50, put 50.1 for 50.4, then you get a new acceleration of 17.0. So it doesn't have an appreciable effect on the angular acceleration.